Okay, so here is our problem. The question is right here. What is the vapor pressure of seawater at 20 degrees Celsius? And this is the key here. We're not talking about pure water here. We're talking about seawater. And to keep things simple, we're just going to think of seawater as basically having, being mostly made of water, but it has a little bit of sodium and chloride ions dissolved in it, and it tells you specifically how much seawater has. And so we want to know what the vapor pressure is, and there's a little bit more information. Vapor pressure of pure water, not seawater, pure water at 20 degrees Celsius, so at the same temperature, is this many atmospheres. So there's our vapor pressure of pure water. And here's what our pretend seawater is made of. And the last bit of information we need to know is that the vapor pressure of sodium and chloride ions is nada at that temperature. In other words, they don't fly up into the air at that temperature. And what we're going to do to figure out the vapor pressure of seawater is we're going to break out Raoult's law. And just in case you don't remember what Raoult's law is, it says the total pressure of a mixture is equal to basically the fraction of all of the pieces multiplied against whatever their vapor pressure is. So for us, it's going to be the fraction, it's going to be the fraction of water molecules times the vapor pressure of water at that temperature, so 0.0231 atm, plus the fraction of sodium ions times the vapor pressure of sodium, which is going to be 0 atms, plus the fraction of chloride ions times the vapor pressure of chloride at that temperature, which is also going to be 0 atm. And so that's a setup. We need to figure out what the fractions are. But those of you who are paying close attention, you'll notice that there are a couple of zeros here. And you know what that means. We are multiplying some number, the fraction of sodium ions, times 0. So it doesn't really matter what this number is. That part is going to come out to be 0. Same thing here. We could spend some time figuring out the fraction of chloride ions that are in seawater, but we're going to be multiplying that against 0, so it doesn't really matter. That's going to be 0 as well. So the only thing that we really need to figure out is the fraction of water molecules in seawater, and we need to multiply that against the vapor pressure of pure water. So let's do that. So what we have to do is we have to figure out the total number of moles of things in our seawater. So that's going to be 53.6 plus 0.56 plus 0.56. And that is going to be a total of 54.72 moles of all things dissolved in seawater. And we need to figure out the fraction of our seawater that's coming from water itself, and that is going to be 53.6 moles divided by 54.72 moles. And if you divide 53.6 divided by 54.72 and you round correctly, it comes out to 0.980. So 98.0% of seawater is made of water molecules. And so this is going to be our mole fraction. That number goes there. So the total vapor pressure of seawater is going to be 0.980 times 0.0231 atmospheres plus a couple of zeros. So that's not really going to change anything. So what is 0.980 times 0.0231 atmospheres? That turns out to be 0.0226 atmospheres. And that is the answer to our problem. That's the answer to what is the vapor pressure of seawater at 20 degrees Celsius. It's this, and it just comes from Raoult's law. And I want to compare this to what the vapor pressure of pure water is at the same temperature. Which one is higher? Well, this one is higher. 0.0231 is a little bit bigger than 0.0226. And so this is a little bit weird. It comes directly from Raoult's law, and it has kind of a big implication, and that is If you have pure water at a certain temperature, it's going to have a certain vapor pressure. But if you start dissolving stuff into the water that can't fly into the air, that is not volatile, if you start dissolving stuff into the water like sodium chloride, it's going to make the vapor pressure of the water go down. It's going to make the vapor pressure of the liquid go down. So if I threw more salt into the water, the vapor pressure would go down more and more and more. And this is related to the previous video where I showed you a container and there was a wall and there was pure water on one side, and there was salty water on the other side. And I said that the water on the salt water side, the vapor pressure was going to be less than the vapor pressure on the pure water side, and this would make the water sort of fall into the right side more. And you can actually put numbers on this. You can actually show people using Raoult's law that if you start dissolving things that don't have a vapor pressure into a liquid, that the vapor pressure of the liquid is going to go down. And this kind of has big implications that we're going to talk about in an upcoming video. The other thing that I want to emphasize before I end this video is it doesn't really matter what you end up dissolving in the water. As long as it's non-volatile, it's basically going to have roughly the same effect, not only on the two chambers, but it's going to have the same effect on reducing the vapor pressure of the water. So if you dissolve more salt into the water, the vapor pressure of the water is going to go down and down and down. And this effect, when it doesn't really matter what you're dissolving, has the same effect. It's called a colligative effect. I'm not a big fan of this word because I can never remember sort of where this word comes from. But basically, colligative effect means that it's an effect that you see on materials that doesn't depend on the material itself. It just depends on how much of the material you're using. So if I throw a whole bunch of salt in, it doesn't really matter what kind of salt I throw in. It's going to have the same effect. It just depends on how much salt I throw in. That's called a colligative effect. And that's the end of the video for figuring out the vapor pressure of seawater using Raoult's law. So see you next time. Bye-bye.
Incredible, unforgettable, to watch you shake your booty, booty to the ground. Yes. It's awful nice, it's paradise. Got me getting up while you're getting down. Everybody says you're a kid.